In number one, it talks about Perry investing in a property that cost him $1,500, and then 5 years later, it was worth double that, $3,000. Then in another 5 years, so 10 years from his original purchase, it was worth double that, so $6,000. So what's happening here is his property every 5 years is doubling, and they want to know what type of function does this represent? Well, this would represent an exponential function, okay, an exponential function, because an exponential function, it goes up by a rate. So here it's going up by 100%. It's doubling every 5 years. So that would be choice one. All right, now number two, that one just wants to know which one represents an exponential relationship. So again, an exponential relationship, it goes up by a rate, or it could also go down by a rate. Okay, if you have exponential decay, it could be going down by a rate. So if we take a look at this first one right here, what's happening is we're starting off at 8, and then in the next term it's cutting in half to 4, and then it's cutting in half in 2. So basically when something is being cut in half, it's going down by 50%. Or if you want to think about with an exponential relationship, you could multiply to get from one term to the next. Well, what we're multiplying here by is 1/2 to get from one term to the next. So choice one is our answer. All right, now in number 3, it says, if the function g of x, which equals a times b to the x power, represents exponential growth, which statement about g of x is false? Okay, so we're looking for what is false, which is not true. All right, so let's start with the first one. It says a is greater than 0 and b is greater than 1. Well, you know what you can do? You can plug a value greater than 0 in for a and a value greater than 1 in for b, and let's see what happens, okay? So I'm going to rewrite this as g of x equals, I'm just going to, since a has to be greater than 0, I'm just going to pick 1. 1 is greater than 0. And then since b has to be greater than 1, I'm just going to pick 2, because 2 is greater than 1. And let's raise that to the x power. Okay, so let's graph this in our calculator, and let's see if it represents exponential growth. All right, so when we graph this in our calculator, I'm just going to sketch a little graph of it over here. It looks like this. Okay, so it is definitely representing growth, and more specifically, let me put some points on here. It's going through the point 0, 1. I'm just going to label this g of x. So let's look back at choice 1. If we pick an a value greater than 0 and a b value greater than 1, yes, it does represent exponential growth. So we're looking for which is false. So choice 1 is out. Okay, choice 2. The y-intercept is 0a. Now, if you look here, we let our a represent 1. And look, it is 0, 1, 0a. So that's also a true statement, okay? So that one's not the answer. Okay, so choice 3, the asymptote is y equals 0. Now remember, an asymptote is a line that the graph comes closer and closer to but never reaches. So see how the graph is coming closer and closer to the x-axis? The x-axis here would be our asymptote. And the equation of the x-axis is y equals 0. Okay, whenever we have a horizontal line, it's always y equals, and wherever it crosses through the x-axis, that's a y equals 0. So that's a true statement. So choice 4 has to be our answer, but let's just make sure. Okay, it says the x-intercept is b0. Well, this graph right here is not going to have an x-intercept because it's never going to touch the x-axis. It'll come closer and closer to it, but we'll never reach it. So this is the false statement. All right, number 4. If $5,000 is put into a savings account that pays 3.5% interest compounded monthly. Okay, so I wrote over here our compound interest formula. Let me just move this up so I have a little bit of room. All right, so if we're going to be compounded monthly, well, that means n, which represents the number of compounds per year, we're going to have to replace with a t. All right, well, let's just go through one step at a time. Okay, so what they want to know is how much money to the nearest 10 cents would be in that account after 6 years. So we're looking for the amount in the account after 6 years. We're looking for the A. So I could write A equals, now P stands for the principal amount that we put into the account, so that would be 5,000. R is the rate, so we want to take this rate and move the decimal place back twice. So that would be 0.035. We said N, since it's compounded monthly, there's 12 months in a year, so it's the number of compounds per year. We could replace the N, both ends, with a 12. And then T would be the time that has passed, which is 6 years. So all you're really going to do is just plug all of this into your calculator. Okay, so when we do, we wind up getting $6,166.51. Now keep in mind they wanted you to round to the nearest 10 cents. So if you round this to the nearest 10, this 1 would round would round down to 50. You do have to say, all right, am I going to round down to 50 or up to 60? Because that's to the nearest 10. So this 1, since it's lower than a 5, we're going to round down. So this will be 50 cents. So that is choice 4. Okay, number 5. It gives us, rather than reading the whole problem with you, it gives us this function, and they want to know if this could be used to represent monthly growth rate. Okay, so let me move this over and give myself a little room here. So what I'm going to do is I'm going to rewrite the function, and I gave myself a little bit of room to put an exponent in here as well as an exponent out here. Now, if we want to reveal monthly growth rate, in front of the T, we put the number of months that fit into 1 year. So since there's 12 months in a year, we're going to put a 12 in front of the T. Now, to compensate for putting a 12 there, because now we've totally changed the value of this function, we need to put a 1/12, which is the reciprocal of 12, on the inside of the parentheses. Okay, so now from this point, all we have to do is just bring everything down other than this. What we're going to do is we're going to plug into our calculator. Okay, so when you plug that into the calculator, it looks like we get 1.00206. I'm just going to round to what the answer choice says. And then you could take everything else and just bring it right down. Okay, so choice 1 would be our answer. Okay, the next one, number 6, is very similar. It says they give us an equation here. They give us a function, d of t, and they want us to take this function and rewrite it in terms of daily interest rate. Okay, so basically all we're going to do is we're going to take the number of days in a year and put it in front of this t. So we'd have to have a 365t. So it'd have to be choice 2 or choice 4. Okay, these two are out. But to compensate for putting a 365 in front of the t, we need to insert its reciprocal on the inside, which is what we see right here. Okay, so we're going to put a 365 in front of the t, and we're going to insert its reciprocal inside. Okay, so choice 4 would be our answer here. They didn't even want you to figure out what this was equal to. Okay, you could just stop once you saw the formation of it. Okay, so number 7. Kellyanne has $20,000 to invest. She puts half the money into an account. So she puts $100,000, $10,000 into an account that grows at a rate of 0.9% compounded monthly. So let's just think about this. All right, so let me just put this down here. So she takes half of the money. So she takes $10,000 and she puts it into an account that is compounded monthly. So let's use our compound interest formula. So 1 plus the rate. So if you take this decimal and move it back twice, that would be 0.009. So 0.009 divided by monthly would be 12. Okay, there's 12 months in a year. And that would be raised to the 12t power. Okay, so let's see, we have 10,000 times, now if you plug all of this into your calculator, you get 1.00075 to the 12t power. So that's what she's doing with half of her money. Now, honestly, you could tell at this point that it is choice 4 because that's the only one that says that. Okay, but let's just keep going. So she takes the other half and she puts it into an account that grows continuously. So remember, if it grows continuously, it's going to be a PERT. And that grows at a rate of 0.8%. Okay, so she takes the $10,000, and if it grows continually, you're going to multiply that by e to the RT power. So if we take our rate, let's take this decimal and move it back twice, it's going to be 0.008, and that's going to be to the t power, which is what this says right here. Okay, so choice 4 is our answer. Okay, so number 8, you can read through it if you want, but what happens is they give us a formula, and they want to know, basically, how could you rewrite this formula to look like one of these? Okay, now, I mean, let's be honest, you can just do this in your calculator. You could plug this, the right-hand side of this equation into your calculator and hit enter, and plug the right-hand side of each of these equations into your calculator and hit enter to show what matches up. All right, let me show you what I mean. Okay, so what I did here was, if you look, I plugged right here. This is the original question. Okay, I plugged that in the calculator. That's what came from the actual question. And you may get something different because it depends on what your x is stored as. I know they use a t as the variable, but I figured in the calculator x is a little easier. And I got approximately 91. Now when I plugged in choice 1, if you look here, this answer, it has an e in it. That e to the 17th, that means you got to move the decimal 17 places to the right in the positive direction. These are not the same, so it's not choice 1. Okay, so as I scroll down, sorry about that, I plugged in, I want to see which gives me about 91. I plugged in choice 2, and it definitely didn't give me 91 point something. I plugged in choice 3, and look at that, that gave me 91 point something. When you plug in choice 4, you don't want to stop. You always want to make sure, which one it is. Choice 4 also doesn't work. This one has an e to the negative 8, which means you have to take the decimal and move it 8 places in the negative direction. So if you kind of use the cheat technique and do it in your calculator, choice 3 would be the answer. Okay, so let's do this by hand now. How do I get this out of here? Let's see. Oh, there we go. Let's toss it to the side. Okay, so if you look at all the answer choices, what you'll notice is that, see how they all have the 100 in front of the parentheses, just like we have here? And see how they have the t all by itself on the outside of the parentheses? That's what we don't have. We need to get this t all by itself on the outside of the parentheses. Okay, so let's just kind of rearrange our equation to do that. So I have a equals, I'm going to take this 100 and bring it down. I'm going to take the 1/2 and bring it down. Now I'm going to rewrite the exponent a little different. There's really a 1 in front of this t. So instead of writing it as t over 73.83, I'm going to take this t and bring it I'm going to take it out of the fraction. I'm going to rewrite this as 1 over 73.83 times t. Now remember, you're always allowed to take an exponent and shift it on the inside of a parenthesis if you want. So I'm going to just rewrite this as 100 times 1/2, and I'm going to put that exponent inside the parentheses. And the reason I'm doing that is so that I have this t all by itself, just like I do in each of the answer choices. Now from here, all you have to do is just plug this into your calculator, and when you plug in 1/2 to the 1 over 73.83 power, you'll see that we get that decimal that matches up with choice 3. So choice 3 would be the answer. Okay, so in number 9, they give us a function right here. They give us an equation, and that says when this equation is written in terms of the number e, so they rewrite it like this with the base of an e, they want us to solve for k. So since this equation can be rewritten in this form, it must mean that they're equal to each other. So let's start off by taking this and setting it equal to this. Okay, so now what they want us to do is they want us to find the approximate value of k. So we need to solve for k. Okay, so I'm just kind of looking ahead here, but we know that this right here, d over 8, is really the same thing as 1d over 8, which if we want to take this d and pull it out of the fraction, we could rewrite this as 1/8 d. Okay, so again, all I did was I took this D and pulled it to the side and rewrote this as 1/8 D. So that's what I have here. Now, if we look at the left-hand side of the equation and the right-hand side of the equation, I mean, see how they both have the 100 right here? And see how they both have an exponent of a D right here? The only differences in these two equations are, let me just kind of box this off in a different color. This and this, right? Because, again, in front of that box I just made is 100, and to the right of that box I just made is an exponent of a D. So the only differences in the equation is this and this. So if we take this and set it equal to this, that can help us solve for K. Okay, so let's solve. So all I'm going to do is I'm going to plug 1/2 to the 1/8 in my calculator. I mean, that's going to give me a decimal that keeps going, so if you prefer to just kind of leave it like this on your paper, you would get a more exact answer in the end. Okay, but, you know, if I do plug that in my calculator, get approximately 0.9170, or again, you can leave it like this. Now, when we have an E, if we want to get rid of an E, what we do is we put an ln in front of both sides of the equation. So I'm going to put an ln in front of both sides of the equation. So that'll leave me with ln of this decimal, which is the approximation of 1/2 to the 1/8 power, equals, and we know these cancel, K. So now all I have to do is plug in my calculator, ln of this right here, actually, I'm going to do ln of answer, because I have that entire answer in my calculator. So when I plug in ln of answer, it tells me that K is approximately negative 0.0866. So that is going to be answer choice 1. Now, if this was a difficult question to comprehend, I mean, a really easy way to do it is if you go back up here to your beginning equation, right? What you can do is you can just pick any number for D. Like, let's say you pick the number 2, right? You could plug this into your calculator, 100 times 1/2 to the 2/8, okay? You could just pick any number you want for D and plug it in and hit enter. Now, on this side of the equation, you're also going to have to use that same number for D. So if you plugged in a 2 here, you can plug in a 2 right here. So you could plug in, after that, 100 times E to that. And you're going to take these answer choices and plug them in one by one for K and see, you know, if you use the same value of D for both sides of the equation, which answer choice, when you plug it in for K, winds up making the left side of the equation equal the right-hand side of the equation. Okay, so here's what I mean. So in my calculator here, I took this, sorry about that. I took this right here, and I just replaced the D with any number I chose. I chose 2, so I plugged in 100 times 1/2 to the 2/8, which is what I did right here. And it gave me 84.0896. Okay, then what I did was I took that same 2 and plugged it in for this D. So I plugged in 100 times E. Now, in place of K, I plugged in the first answer choice, which said negative 0.087. So I plugged in 100 times E to the negative 0.087, and again I replaced that D with a 2. And when I hit enter, what you could see is these answers. They're not exact, but that's because this is a rounded answer of K. But they're very, very close. If I were to replace this K with any of the other answer choices, they wouldn't match up at all. So choice 1 is the answer. Okay, if we take a look at number 10, they want us to use the half-life formula. It says that iodine 131 has a half-life of 8 days. Okay, so since it has a half-life of 8 days, this is the formula we're going to use. So we could replace this H with an 8. All right, so a patient is given a 20 milligram dose. So that's the initial dose. That can go in for the P. And we want to know, and they're allowed to take another dose when 12% of the original dose remains in the body. All right, so let's first figure out what 12% of the original dose is. So 12% of the original dose was 20 milligrams, 12% of 20. Okay, and 0.12 times 20 is equal to 2.4. So that's what we're going to plug in for the A. Okay, that's the amount that remains from the initial amount after a certain time has passed. So what they want us to figure it out is how long to the nearest day does the patient have to wait before taking another dose. So we're looking for the T. Okay, so the amount, the ending amount, the A is 2.4. Okay, that's the amount that remains in the body when they're allowed to take another dose. The initial amount, the P, is 20. The T is what we're solving for. And the half-life, they told us, is 8 days. All right, so we're just going to solve this. So since our exponent is where the variable is, we need to get this base, this 1/2, that contains the exponent by itself. So that means we got to get rid of this 20. So in order to get rid of the 20, the only way to do that would be to divide both sides of the equation by 20. So 2.4 divided by 20 brings us to 0.12. Okay, that's that 12% that remains. So 0.12 equals, and then you could bring down the 1/2 to the T over 8 power. Now, we know that we're going to have to use logs because our variable is in the exponent spot. So what we're going to do is we're going to put the word log in front of both sides of the equation. And the reason we do that is because the power rule tells us you can take a power and bring it to the front of the word log. Okay, so let's rewrite this. I'm going to bring down log of 0.12, and I'm going to take this power and bring it to the front of the word log. So it'll give me T over 8 times log of 1/2. Okay, so we're trying to get the T by itself. So let's first get rid of the log of 1/2 that's being multiplied to the T over 8. So since it's multiplication in between here, to get rid of the log of 1/2, we're going to divide both sides of the equation by log of 1/2. All right, so now this you're going to have to plug in your calculator, and it is going to give you an ugly decimal, but leave that number in your calculator. So when you plug in log of 0.12 divided by log of 1/2, it gives you approximately 3.0589. Again, leave that entire number in your calculator because we're going to work with that in a minute. Okay, so if we want to get this T by itself, I mean, honestly, the easiest way, since we have an 8 in the denominator, if you multiply both sides of the equation by what's in this denominator, right? If we multiply both sides of the equation by 8, what's going to happen is this 8 on bottom cancels with, this is really 8 over 1, cancels with the 8 on top, leaving us with just T. And when you multiply the value in your calculator times 8, it's going to give you approximately 24.4711. Okay, so how long to the nearest day does the patient have to wait before taking another 20 milligram dose? Well, within the 24th day is when there is 12% of the medication left. So to the nearest day, it's going to be 24 days. Okay, it occurs within the 24th day. Okay, so number 11 also deals with the half-life formula because it says here that the substance has a half-life of 1.8 hours. Okay, so they want to know what is the approximate amount of sodium iodide 131 that will remain in the body after 18 hours. So we want to know after 18 hours have passed how much remains. So that 18, I'm going to replace the T with. All right, so let's kind of just start making our exponent up here. Now the H, the half-life, they tell us is 1.8 hours. So I'm going to replace the H with a 1.8. Okay, now P stands for the initial amount. Now if we look at our table here, it says that after one half-life, 139 units of this substance remained. So before that half-life occurred, wouldn't there have been double of this occurred? So if this chart had, like, let's say another column, if we had 0 half-lives, right, you would have to double this amount. So if you did 139 times 2, that gives you 278. That's actually going to be the initial amount. That's what we're going to plug in for P. Okay, so all you really have to do is just plug this into your calculator and see what you get. And when you do, you get approximately 0.27148. So that would be choice 3. Number 12 asks us to determine the solution to the nearest thousandth. Okay, so if we look here, we can see that what we're solving for is an exponent. And since we have an E in our problem, we're going to have to use ln to solve. Now, first thing we're going to have to do is we're going to have to get this e to the 0.4x power all by itself. So we have to get rid of this 148. All right, so since it's 148 times e, the opposite of multiplication is division. So let's first divide both sides by 148. All right, so on the left side of the equation, the 148's cancel, so we can bring down the e to the 0.4x. And then if we plug in our calculator, 8,486 divided by 148, it'll give us a decimal. So rather than rounding on our paper, let's hit math, enter, enter. And in simplest form, it looks like we get 4,243 divided by 74. Okay, now as we said before, to get rid of an e, we want to throw an ln in front of both sides of the equation. Okay, now, the reason we do that is because when you have ln of e to some exponent, it's always equal to just that exponent. You can think about it like the ln and the e canceling each other off and just bringing down the exponent. So if you want to go like this, you can do that. And then we'll bring down the right-hand side of the equation. Okay, so now from here, we're just going to divide both sides by the number in front of the x. And when we do, they cancel out on the left, leaving us with x. And then here, you're just going to plug this in your calculator and make sure you round to the nearest thousandth. So you wind up with 10.122. Okay, if we look at number 13, we also see we have an e in the equation, and in this one they want us to solve for t. Okay, it says t equals. All right, so let's get the e that has the exponent on it by itself. So we need to get rid of the a. So we're going to, since it's a times e to this power, we're going to, the opposite of times is division. Okay, the opposite of multiplication is division. So we're going to divide both sides by a. All right, so those cancel, leaving us with e to the bt power equals c over a. Okay, now to get rid of the e, we're going to put an ln in front of both sides of the equation. All right, so we have the ln and the e are going to cancel, and we can bring down the bt. And then on the right-hand side of the equation, we have ln of c over a. I'm just going to put that in parentheses because I'm looking at all the answer choices, and I see parentheses there. Okay, so now to get the t by itself, all we have to do is just divide by this b. So that leaves us with t equals just ln, I'm just going to literally recopying this, ln of c over a divided by b, which matches up with choice 3. Okay, number 14, they give us some information, right? We have 950 bacteria growing continuously at a rate of 4.75% per day. Now, when we see this word continuously, that's coming right out and telling us we're going to use the compound and continuous formula, APERT. Okay, A equals P times E to the RT power. So the first thing we want to do is write an exponential function, n of t. So in place of A here, we're going to have n of t. So let's write that, n of t equals, okay, so in place of the P, we know we started off with 950 bacteria. We want to leave the E as our base. E stays as E. The rate is 4.75, so if we change that to a percent, you move the decimal place back twice, so that'll be 0.0475. And we want to leave that in terms of t, because we want to be able to plug in different times into this function so that you could see how much bacteria is left, okay? So, and that's why we have a t here, the number of bacteria in terms of time, so n of t. Okay, so that's the answer to the first part. Now, it also says to explain the reason for your choice of base. All right, well, whenever you see continuously, we know we're going to be using this formula, and the base with this formula is E. Okay, so E is our base because the population of bacteria grows continuously, okay? So whenever you see continuously, you know that E is your base. This is your formula you're using. Okay, then it says to determine the bacterial population after 36 hours to the nearest bacterium. All right, so they want us to use this formula and figure out how much bacteria will be left after 36 hours. So we're going to have to plug in a number for T for the time. Now, if we look here, this is growing at this rate per day. So since this is in terms of hours, we're going to have to figure out how many days have passed in 36 hours. Okay, so what I did was I took the 36 hours that passed and divided it by 24 hours in a day, and that means 1.5 days have passed. So 1.5 is what we're going to plug in for t, for the time. Okay, so all I did was just plug this in my calculator, and this is what it gave me. Now, you're not going to have a decimal of a bacterium, so you're just going to have to round this really to the nearest whole number here, because we just want to figure out the population after 36 hours. So this would round down to 1,020 bacterium. Okay, so in number 15, again, they're talking about compounded continuously, so we're going to be using our APERT formula. All right, so it says determine to the nearest tenth of a year how long would it take an investment to double at 3.34% interest, compounded continuously. Now, they're not telling us how much we started off with, so you can pick any number you want to start off with. Like if you pick, let's say, $100 to start, and you doubled that, you would put $200 here. Let's say you picked $1,000 to start off with for P. Well, if you doubled that, you would put $2,000 here. Even if you picked a 1 to put in place of T, if you double 1, doesn't that give you a 2? So I'm going to do that. I'm going to put 2 in place of A and 1 in place of P. And now they tell us the rate, so I'm bringing over the E. They tell us the rate is 3.3 3/4%, which is 3.4 is 0.75%. So if we move the decimal place twice to the left, that becomes 0.0375. So that's what we'll plug in for the rate. And we're going to raise that to the t power. Okay, and again, like I said, if you want to plug a 100 here and double that to 200, you can. If you want to plug a 5 here and double that to 10, you can. As long as this number is double whatever you put here, you'll get the same thing in the end. Okay, so let's solve. So we want to get this base of E all by itself. So to get rid of the 1, you can divide both sides by 1 if you want. So 2 divided by 1 is 2, and I'll bring down the E to the 0.0375 t power. Now, just like in some of the examples above, to get rid of the E, we're going to put an ln in front of both sides of the equation. So these cancel, and we can bring down the 0.0375 t. And on the left-hand side, we can bring down the ln of 2. So then to finish solving for t, just divide by the number in front of the t. And we're going to just plug that in our calculator. You don't have to use the approximate symbol. I like to sometimes because, we're not writing the exact answer. But when you plug this in your calculator, you get approximately 18.4839. So 18, I'll just write that for now, 18.4839. Okay, so they want it to the nearest tenth of a year. So to the nearest tenth of the year, in order for that to double, you would round up to 18.5 years. So in number 16, the first thing they're asking us to do is they're asking us to determine Dom's mortgage payment with no down payment. So if he doesn't put any money down, how much will his mortgage payment be? Now they say here that the mortgage payment is represented by M. So M represents the mortgage payment. So M is what we're looking for. So I'm going to write M equals, and then we're just going to plug in numbers for everything else. All right, so P is the principal amount. So if he's not putting any money down, the principal amount is how much he wants to borrow. It's the initial amount that he's borrowing from the bank, which is the price of the home. So that'll be $485,600. Okay, so we're going to multiply that by, I'm going to put this in parentheses. I know they just use like a little multiplication dot, but I'm just going to put parentheses. Same thing, right? All right, so now first thing we see is R. So R is the rate. So here's our monthly interest rate. So what we want to do is we want to take this decimal and move it 2 places to the left. So when we do, it's going to be 0.00415. Okay, and then in parentheses, it says 1 plus the rate. So if I do 1 plus this decimal, it's just going to be 1.00415. If you prefer to write 1 plus 0.00415, you can. It's the same thing. Okay, so now N, the exponent, stands for the number of monthly payments. All right, well, let's see. We're taking out he's taking out a 15-year mortgage. And since they want the number of monthly payments, there's 12 months in a year. So 15 times 12 would be 180. So that's going to be our exponent. Okay, and then in the denominator of the fraction, again, it's 1 plus the rate. So you could either write 1 plus 0.00415, or you could just write 1.00415. And we're raising that to the n power, which we said is 180, and then minus 1. Okay, so all we have to do here is just literally take this whole thing, and since everything is numbers, you could just plug everything into your calculator. Now here they want it to the nearest dollar. So when you plug this in your calculator and you round to the nearest dollar, you wind up getting $3,835. All right, so that's the answer for the first part. Now, the second part wants you to algebraically determine and state the down payment. So we're looking for the down payment to the nearest dollar in order for his mortgage payment to be $3,000. Now remember, the mortgage payment, right here, mortgage payment is represented by M. So we're going to replace this M with a 3,000. So we have 3,000 equals. Now, if we're looking for what his down payment should be, what we're really looking for is, within this formula, is the P. We're looking for how much he wants to borrow. Because if we could figure out how much he wants to borrow from the bank, all we have to do is subtract that from the price of the home, and that'll tell us how much money he put down, how much money he gave the bank ahead of time off the price of the home, so he didn't have to borrow as much. Okay, so what we're solving for here is the P. So when you're looking for the down payment, you're really solving for the P within the formula. Okay, now everything else within this formula is the same as above, so I'm just going to copy all that down. Okay, so there we go. So then basically we have 3,000 equals P times whatever this is equal to. So if we want to get the P by itself, we have to divide both sides of the equation by this. If you prefer to plug this in your calculator first and then write it as like a rounded decimal on your paper, you can. As long as in your calculator you don't do 3,000 divided by that rounded decimal. You would want to do 3,000 divided by this entire answer. Okay, so I'm going to actually do that just so you can see how we do this. So I'm going to plug this into my calculator. Okay, so when I did that, I got this right here to be approximately 0.0079. So if you want to write it like that for now, you can. We could say 3,000 equals P times 0.0079. But in your calculator, don't do 3,000 divided by 0.0079. You want to do 3,000 divided by answer, this entire answer that you got from your calculator. Okay, so you want to divide it by not just these 4 digits, the entire decimal that your calculator gave you. All right, so let's do this. Let's divide it. On the paper, we're just going to show that we're dividing it by this rounded answer. But in the calculator, we're not going to use the rounded answer. We're going to use the whole entire answer. Okay, so that leaves us with, on the right-hand side, P, and on the left-hand side, well, to the nearest dollar, let's see, this is going to round to $379,866. Okay, so now, this is P. This is the principal. This is the amount we want to borrow from the bank. If we want to figure out the down payment, how much money that Dom put down ahead of time so we wouldn't have to borrow as much from the bank, what we're going to do is we're going to take the price of the home right here and we're going to subtract the principal, and that'll give us the amount that he had put down. Okay, so when we do that, we take the price of the home and subtract up how much he's borrowing from the bank, and this right here is his down payment on the house, rounded to the nearest dollar. Okay, now in number 17, Donovan wants to buy a car, so he's going to take out a loan, and they give us this formula. Now it says Donovan wants to keep his monthly payments at $400. Okay, now if we look at the formula, it says the PMT stands for the monthly payment. So we want to keep this at 400. So I'm going to replace that with 400. So right after the equal sign, that's going to be a 400. And then let's keep reading. Determine an appropriate down payment to the nearest dollar with a monthly percentage rate of 0.625%. So this is going to go in for I, the interest rate per month, for a car that originally cost $36,000. Okay, now if you notice here within the formula, there's nothing that represents down payment, because in order to find the down payment, what we do is we take the amount, the P sub n, the amount that you borrow, and you subtract that from the price of the car, and that's what gives you the down payment, okay? So the price of the car minus the amount you want to borrow is equal to the down payment. Okay, so just like in the last example, when we want to find the down payment, we need to figure out how much he's going to borrow to help us with that. Okay, so let's plug in everything we know here. So if I follow this formula, it says, in parentheses, 1 minus, and then 1 plus the interest rate. Now, the interest rate is 0.625%. So if we move this decimal place back twice, it's going to be 0.00625. So you could write 1 plus 0.00625, but isn't that the same as just 1 point and then 0.00625? You don't have to put that plus sign in there, because when you combine them together, this is what you get. And that's going to be raised to the negative n power. Now, n is the number of monthly payments. So since he's borrowing the car for 5 years, and there are 12 months every year, that means altogether, if you multiply those, there's going to be 60 monthly car payments. So we're going to raise this to the negative 60 power. Right, and that's going to be over just I, which is, we said before, 0.00625. So what we're looking for here is the P sub n. We're looking for the amount borrowed. Okay, so we can plug this in our calculator, and they want it to the nearest dollar. So to the nearest dollar, we get P sub n equals, and I'm getting $19,962. Okay, so let's go to our little formula over here. If we want to figure out the down payment, we take the price of the car, and we subtract from that the amount that we're going to borrow. Okay, so the price of the car is, I'm just going to do this off to the side here, $36,000. And the amount that we need to borrow, that he needs to borrow from the bank, is $19,962. So when we subtract this will give us our down payment. So our down payment, sorry, that's a really bad dollar sign, is $16,038. That's how much, Donovan has to put down on his car in order to keep his monthly payments at $400 per month. Okay, so in number 18, Tony is evaluating his retirement savings. He currently has $318,000 in his account, which earns an interest rate of 7% compounded annually. Okay, he wants to determine how much he will have in the account in the future, even if he makes no additional contributions to the account. So what they want us to do here is they want us to write a function, a of t, to represent the amount of money that will be in his account in t years. Okay, now because we see compounded annually, remember, our compound interest formula looks like this. Okay, so instead of a, they want us to write a of t. So a of t equals, now in place of the p, that's going to be the initial amount, which is the $318,000. Okay, then it says here, 1 plus the rate. So the rate, 7%, we know if we move the decimal place back twice, we could write as 0.07, divided by n. The n is the number of times per year that it's being compounded. If it's being compounded annually, it's only being compounded once per year. So if we take 0.07 and divide it by 1, isn't that still just 0.07? And if we add 1 to that, wouldn't it just be 1.07? Okay, so 1 plus 0.07 divided by 1 is just 1 plus 0.07, which is 1.07. So that's what I'm just going to write in parentheses to make it a little easier, 1.07. And then we're going to raise that to the n times t power. Well, n, we already know is 1, right? It was compounded annually means once a year. So 1 times t is just going to be t. So here's our formula, kind of in simplest form, if you want to say, with everything combined in the first part. Now, in the second part, they want us to graph A of t, where t is between 0 and 20 inclusive. So they want us to plot all these points between 0 and 20. Now, I mean, you don't have to plot every single point, but you do have to start where t equals 0, and you do have to end where t equals 20. So you want to graph as many that it's going to, you'll be able to determine the shape of the graph. All right, so let's see here. First thing we're going to have to decide, sometimes it's the hardest, what to number by along the y-axis, which is here called the A of t axis, and the x-axis, which is called the t-axis. Now, since we have to number from 0 to 20, and there's 20 boxes, it makes most sense just to number each box, representing the number 1. So this would be 0, 1, 2, 3, 4, and so on. If you don't want to squeeze all the numbers on here, you can just put every other number. That's fine. Okay, so that one wasn't that bad. Now, when we go to number the y-axis, what we're probably going to want to do is we're going to want to take our function that we see up here, and you're going to want to go to y equals in your calculator and plug that in. And then the money's going to be increasing. So you're going to want to figure out what's the y value or what's the A of t value when the t value is 20. How high is his account going to reach? And that's going to help us decide, what to number this by. Okay, so here's what I mean. I went to y equals and I plugged this function into my calculator. And if you go to second graph and scroll all the way down until the x value, or in this case really the t value is 20, you'll see, this might look a little funky how it's written here, but if you just use your cursor and scroll over, you'll see that y value, or the A of t value, is actually 1,230,560. Okay? So this is going to get pretty high. Okay, so now what I'm going to do is, instead of using this number, because this is kind of like, this is going to be hard to, kind of space out on our graph here, I'm going to take this value and round it up a little. I'm going to round it up kind of high. I'm going to make it 1,500,000. So if I take 1,500,000 and divide that, let me see if I can move this. Good, okay. So here we go. If I take this rounded up value, so the 1,500,000, okay, I'm going much higher than I need, and divide it by the 20 boxes that are here. All right, that's going to tell me what each of these boxes should represent. Okay, so this is equal to 75,000. Okay, so what I'm going to do is, I'm going to and if you didn't do it like this, if you didn't do it like I did here, you could just do, I guess, trial and error until you get something to fit. But I'm going to let each of these boxes represent 75,000. So this would be 75,000, 150,000. I'm just going to keep adding on 75,000. So this would be 225,000, and then 300,000, and so on. Now, I don't think I'm going to be able to fit all that, so I'm going to label every other box. So we said this was 75,000, so the next one up would be 150,000. So let's label that 150,000. Okay? Or I could just say, all right, every two boxes is going to be another 150,000. That's easier to label it, right? So if this is 150,000, then two boxes up would be 300,000. All right, and then you can just keep numbering these. So if I added another 150,000, that would give me 450,000. And then just keep going. Okay, so then 600,000. Okay, so I finished numbering. I actually stopped at 1,350,000 because I knew that was higher than this number. And then I labeled this. This is kind of messy, but I had to squeeze it in here, money in dollars. Okay, so from this point, you're just going to plot all of these points. Or you know what? You can just plot every other point. If you want to just plot the t values, like the even t values, you can do that. Plot every other point and just do your best to estimate where it would go. I mean, you're not going to be exact because think about it. If one box represents 75,000, you're not going to get exact, but you're going to get, as close as you can. Okay, so this is what my graph looked like. I did my best to estimate, each point, and you could see that the graph here is growing exponentially. It's not growing at a constant rate. Okay, it's growing at an exponential rate. Okay, now for the last part, Tony's goal is to save $1 million. Determine algebraically to the nearest year how many years it will take for him to achieve his goal. Okay, so if he wants to save $1 million, we're going to plug that in for A of t. Okay, the amount that he will have in the account after a certain time has passed. So for the left-hand side of the equation, we're going to plug in 1 million. And then I'm just going to copy down the right-hand side of the equation. That's supposed to be a comma. Okay, so we're going to solve this. Now we know since we're solving for an exponent, we're eventually going to have to use logs, but before we do, we have to get the base that contains its exponent by itself. So to get this by itself, let's first divide both sides by the 318,000. Okay, so if you were to plug this into your calculator and then hit math, enter, enter, it looks like it simplifies to 500 over 159. And that's going to be equal to 1.07 to the t power. All right, now we could throw the word log in there. So we're going to take log of this fraction, and we're going to take log of 1.07 to the t power. And the reason we do that is so that we can move the power to the front of the word log. Okay, so now we're no longer going to have an exponent. We're going to have the left-hand side of the equation being equal to t times log of 1.07. Okay, and then to get the t by itself, we're going to just divide both sides by log of 1.07. And those will cancel, leaving us with just t. Okay, now when we plug this into our calculator, we get, I'm going to write the approximate on the paper, we get approximately 16.9336. And they want to know to the nearest year how long will it take him to achieve that. So it's going to take him 17 years. Okay, now it also says here to explain how your graph of A of t confirms your answer. Okay, so if we look at our graph here, let's say I'm going to go to year 16 and follow that up, we'll see that it's kind of hard to tell off the graph here, but it looks like it's going to be under 1 million, okay, because if this is 900,000 here, and we know that each box represents 75,000, this would be up here 975,000. If we follow 975,000 over, see how year 16 is below that? So it didn't reach 1 million. But then when we get to 17, it looks like it's up here. And if you go to your table of values, you will see at 17 years, your y value, which is your A of t value, is above 1 million. Okay, so all we have to do is just write this out in words. Okay, so this is what I wrote here, right down here. The graph of A of t confirms my answer because at year 16, we could see that the account hasn't reached 1 million yet. At year 17, the graph surpasses 1 million. Okay, so it'll take him 17 years. Okay, so in number 19, Lucas wants to invest his money in an account that is compounded quarterly. So since it's compounded quarterly, we are going to be using our compound interest formula. Okay, now, it says here, they want us to write a function, A of t. So instead of A equals, we're going to have A of t, the amount that's in the account in terms of time. And that's going to be equal to P, which is the principal, which is the $5,000 that he's investing. And then times 1 plus, the rate is 3.25%. So if we take the decimal and move it back twice, it'll be 0.0325. Divided by n. N is the number of times it's compounded per year. So it's compounded quarterly, so that would be 4 times per year. So we could replace both of the n's with 4s. And we want to leave that to the t power. Actually, let me just make that 4 a little better. We want to leave the t in the exponent because they want us to leave it in terms of t. Okay, they want us to leave it in t years. So I'm going to box this up because this right here is answering the first part of the question. This is the function that they wanted us to create. Now after that it says, algebraically calculate the number of years to the nearest tenth of a year it will take Lucas to double his investment. So if he's investing $5,000, if you double that, he wants it to grow to be $10,000. So I'm going to replace the A of t with 10,000. Okay, now this is up to you. If you plug what's in the parenthesis here in your calculator, it does give you a nice clean decimal that stops at terminating decimal. It gives you 1.008125. If you want to write it like that, you can. Or if you prefer to leave it as you wrote it in the beginning, if you prefer to leave it like this, you can. All right, so now we're solving for an exponent, which we know we're going to have to eventually use logs. But before we do, we have to get the base that contains that exponent on it by itself. So we need to get rid of this 5,000. So since this is 5,000 times the number in the parenthesis raised to the 4t power, the opposite of multiplication is division. So we're going to divide both sides of the equation by 5,000. All right, so 10,000 divided by 5,000 is 2, and I'm just going to bring down the right-hand side of the equation. Okay, so now that we got the base that contains that variable exponent on it by itself, now we could throw the word log in front of both sides of the equation. Because the power rule tells us we could take a power and bring it to the front of the word log, and then it will no longer be a power. It will no longer be an exponent. Okay, so I could take this 4t and bring it down in front of the word log. And then I'm just going to, after this, I'm going to take the left-hand side of the equation and just bring it down. Okay, so if we want to get the t by itself, we're first going to divide by log of that decimal, so log of 1.008125. So on the right-hand side of the equation, that leaves me with 4t. And I'm going to use the approximate symbol because this you're going to have to plug in your calculator. And on your paper, we could write it to 4 decimal places. But even though I'm writing it to, at least 4 decimal places on my paper, I want to use that entire number that my calculator gives me to finish solving. So to get t by itself, we're going to have to divide both sides by 4. So in my calculator, I don't want to plug in this rounded number on my paper divided by 4. I want to use that entire number that's in my calculator and just hit divided by 4. All right, and when I do, it shows me that t, I'm just going to kind of come over here. It shows me that t is equal to approximately 21.4141 years. Now we have to decide which way to round because they want us to round to the nearest tenth. So we have to say, am I going to round this down to 21.4 or am I going to round it up to 21.5? Now if you were to round to the nearest whole number, this 1 tells us to leave it at 21.4. But think about it. He wants his investment to double. If you round down, not enough time will pass for the investment to double. Okay, less time will pass, so they'll be under $10,000. Let me show you what I mean in my calculator. Okay, so what I did was I took this original function here, and I replaced the t with a 21.4, and then underneath it, I replaced the t with a 21.5. Now you'll see if we were to round to the nearest whole number, 21.4, if we were to round down, we wouldn't have quite doubled the account yet. There'd be less than $10,000 in the account. Whereas if we took this and rounded up to 21.5, he will have surpassed the $10,000. He will have doubled the money in his account. So we're going to have to round up to 21.5 in order for that to happen. So 21.5 years would be the answer to the nearest tenth in order for his account to double. Okay, so number 20 is a Newton's law of cooling problem. So they give you the formula here. They tell you what everything stands for. And you just basically have to read and plug in, what goes where. Now in part A, it says, if the temperature of the Jell-O was after 20 minutes is 60 degrees, find the decay constant. So what we're looking for is we're looking for the K. So that means we have to plug in numbers for everything else. All right, okay, so let's just read and see what everything else stands for. All right, so it says that after mixing Jell-O, it is placed in the refrigerator to cool where the constant temperature is 36 degrees. Okay, so we're placing this Jell-O in a refrigerator where the temperature where it's being placed is 36 degrees. when placed in the refrigerator, the temperature of the Jell-O was 85 degrees. Okay, so this Jell-O was originally 85 degrees, so that's going to be T sub 0. That's going to be the initial temperature. So in place of T sub 0, we can plug in 85. And since we're placing it in the refrigerator, that is 36 degrees, this 36 right here is going to be T sub A, the temperature of the surroundings. Okay, that's the surroundings where we're putting it. So wherever we see a T sub A, we can plug that in using a 36. Okay, now we already said that the K is what we're solving for. Okay, it said to solve for the decay constant. And then, let's see, in place of T, well, that's going to give this question is what's going to give us this. If the temperature of the Jell-O after 20 minutes is 60 degrees, what that means is after 20 minutes has passed, the temperature is now 60 degrees. So we're going to plug in 20 for the time. 20 for the time. And after the 20 minutes, this temperature, the temperature after a certain time, is 60 degrees. So we'll plug in 60 here. Okay, so now this is what we're going to solve. All right, so let's first subtract 36 from both sides. So that's going to leave us with 24 equals. Now, if you want to combine these, 85 minus 36 is 49. You could do that. You could write this as 49e to the negative 20k. I'm going to put the 20 before the k. So again, if you combine the 85 minus 36, that'll give you 49. And then I'm just going to bring everything else down. E to the, and since negative k times 20 is negative 20k, I'm going to write it like that. Okay, so we want to get this e by itself because it has a variable exponent on it, so that's what we're solving for. So to get rid of the 49, we would just divide both sides by 49. And just so that I don't have to round, I'm going to just leave this fraction as 24 over 49. And I'm going to bring down the e to the negative 20k power. Okay, so now to get rid of an e, we put an ln in front of it. And if we do that to the right-hand side of the equation, we also have to do that to the left. Okay, the reason we put an ln in front of an e is because ln of e to any exponent is just equal to that exponent. You can think about this as, canceling each other off and just bringing down the exponent. Okay, and I'm going to bring down the left-hand side of the equation as well. And then to get k by itself, let's just divide both sides by negative 20. Now, my paper actually says if the temperature of the Jell-O after 20 minutes is 60 degrees, find the decay constant. This right here would be the decay constant. I know in your paper it does say to round to the nearest thousandth. So what you're going to do is you're going to plug this in your calculator and just round that to the nearest three decimal places. So when you do, you wind up getting, let's see, k is equal to 0.036. Okay, so that's the answer to part A. That's the decay constant to the nearest thousandth. Okay, so now in part B, they want us to, it says, how long will it take for the Jell-O in the refrigerator to reach a temperature of 40 degrees? Round your answer to the nearest minute. Okay, so if it's going to reach a temperature of 40 degrees, we're going to replace the T of T, the temperature after a certain time, with a 40. Okay, and then we're going to solve for the T, how long that takes. All right, so let's plug in our numbers here. So for part B, we're going to replace the left-hand side of the equation with a 40. We want to know how long will it take to reach 40 degrees. The T sub A is still 36. That's still our surrounding temperature, the temperature of the refrigerator. The initial temperature of the Jell-O is still 85. All right, now this time we know the K. Now don't forget about the negative in the formula. And we know that K is equal to 0.036. So let's plug that in, 0.036. And we're solving for the T, the lowercase t, how long it takes to do that. All right, so we're going to solve this equation the same way we did in part A. Let's first subtract 36 from both sides. So that's going to leave us with 4 equals, and again, if you combine 85 minus 36, that gives you 49. So 4 equals 49, and then you can bring down the e to the negative 0.036 t power. All right, we again want to get that e by itself, so we're going to divide both sides by 49. and I'm just going to leave the left-hand side of the equation as 4 over 49. It kind of looks like a 9, but that's a 4. And then I'm going to bring down the e to the negative 0.036 t power. Now again, to get rid of an e, we put an ln in front of it. And if we do that to the right-hand side of the equation, we also have to do that to the left-hand side of the equation. So on the right-hand side of the equation, just like in part A, the ln and the e cancel, allowing us to just bring down the exponent. And let me bring down the left-hand side of the equation. Okay, and to get the t by itself, you're going to divide by the number in front of the t. So we're dividing both sides by negative 0.036. And when we plug the left-hand side of the equation, when we plug this into our calculator, I get approximately, let's see, 69.5979. Now, just to go back to the question, how long will it take for it to reach a temperature of 40 degrees? So we have to round up because it has to completely reach the temperature of 40 degrees, and then they want us to round that to the nearest minute. So if we round this up to the nearest minute, that will take 70 minutes. Okay, number 21 is very similar to the previous one. This one deals with Newton's law of cooling, and they tell us that the brewing pot temperature of coffee is 180 degrees. So the coffee was brewed, and it reached a temperature of 180 degrees, and it was then placed in a room that was 76 degrees. So this would be our surrounding temperatures. That would be the T sub A. And then this, 180, would be the initial temperature. That would be the T sub 0. And when we read part A, it says after 5 minutes, so that is going to be our lowercase t, the time, the temperature of the coffee is 168 degrees. So that's going to be the temperature it reaches after t minutes, after 5 minutes. So that's going to be the T of t. That's going to be the temperature of the object after t minutes. All right, so let's just plug in our numbers. So if we look at this formula here and place a T of t, we can plug in 168. And then equals, we said that the T sub A is equal to 76. And then plus T sub 0, the initial temperature, we said is 180 degrees. Minus, again, T sub A, which is 76. Times e to the negative k. That's what we're looking for, the k. And in place of the lowercase t, the time that has passed, we can plug in 5 for minutes. All right, so this is what we're going to solve. All right, I'm going to slide this up so it gives me a little more room. All right, so I'm first going to just subtract 76 from both sides of the equation. So that'll leave me with 92 equals, and if you like to combine this, 180 minus 76 is 104, times e to the, and negative k times 5 I'm going to write as negative 5k. All right, so now, since we're solving for a variable, for an exponent, we need to get its base by itself. So I need to get this e by itself. So to get rid of the 104, I could just divide both sides by 104. So 92 divided by 104, you can leave that as that fraction, or if you want to simplify it, plug it in a calculator, math enter, or if you want to do it, by hand, that simplifies to 23 over 26. Okay, and then we can bring down the e to the negative 5k. Okay, so just like we saw in the last one, to get rid of an e, we put an ln in front of it. So if we do that on the right-hand side of the equation, we have to do that to the left-hand side of the equation. Okay, so the ln and the e, if you have ln of e to some power, it's equal to just that power. Basically, you can just cancel those off and bring down the exponent. And then you can also bring down the left-hand side of the equation. And then to finish solving for k, we're just going to divide both sides by the number in front of it. Okay, now this is to find k to the nearest tenth. Oh wait, I'm sorry, my paper says tenth, but yours says 10,000, so let me change that. Okay, so if we plug this into our calculator and round to the nearest 10,000th, that will give us 0.0245. All right, so there we go. Okay, so now part B. I'll do that right over here, part B. How long to the nearest minute will it take for the coffee to reach a serving temperature of 155 degrees Fahrenheit? Okay, so this time we're looking for how long. So we're looking for the lowercase t. So we have to plug in numbers for everything else. In place of t, the temperature after a certain time has passed, this time is equal to 155. Okay, now on the right-hand side of the equation, the T sub A is still 76, right? That's the temperature of the surroundings. The initial temperature was 180, the surroundings, again, 76. And now we know the K. The K we found down here to be 0.0245, so let's plug that in for K. And now we're just going to solve this for T. And I mean, whether you're solving for K or T, you're really solving for the exponent. So we're going to solve this the same exact way. All right, so let's just first subtract 76 from both sides of the equation. All right, so that'll give me 79 equals, and then when we combine these two numbers, you get 104 times e to the negative 0.0245t. And again, we have to get the e by itself, so let's divide by the number in front of the e. All right, so 79 over 104 doesn't simplify, so I'm just going to leave it like that rather than write it as a rounded decimal on my paper. And again, to get rid of the e, we put an ln in front of it, which if we do that on the right-hand side of the equation, we also have to do that on the left-hand side of the equation. Now, the reason we do that is because ln of e to this power is equal to just this power. The ln cancels off the e for us. So it's going to leave us with negative 0.0245 t equals, and just bring down the right-hand side. Okay, and then to finish solving for t, just divide by the number that's in front of it. And when we plug this into our calculator, we wind up getting approximately 11.2. Okay, now here's the deal. It says, how long will it take for the coffee to reach a serving temperature? And they want us to round to the nearest minute. If we round this down to 11 minutes, it's still going to be too hot to drink. So what we're going to have to do is we're going to have to round up to 12 minutes. Okay, number 22. Now, let's be honest, this is multiple choice. If you wanted to, you can just plug this whole thing into your calculator and hit enter, and then plug the answer choices into your calculator one by one and hit enter and see what matches up. Okay, but I'm going to do this by hand. So let's see, with this first expression here, the square root of 16 is 4. And then the square root of x squared is just x, right? Because doesn't x times x give you x squared? Okay, so that one wasn't too bad. Now for right now, I'm going to just bring this down, because usually what you want to do is try to get terms out of radical form so that you can combine them, and this is already out of radical form, so I'm just going to bring that right down. All right, and let's bring down the plus sign, and let's see what we can get out of the radical here. Well, the cubed root of 8 is 2, right? 2 times 2 times 2 is 8. Now here, I mean, the cube root of x to the 5th, this is not a perfect cube, so I could simplify that, but I'm going to try to get this out of radical form to make my life a little bit easier. So if I were to get this out of radical form, I would do power over root. I could rewrite this as x to the 5 over 3, power over root. So x to the 5/3. Okay, so now let's see what we have to work with here. All right, so let's first multiply these two terms. So if you want to put a 1 in there, you can. So we multiply the numbers in front. 4 times 1 is 4. And then if we're multiplying terms with the same base, we add the exponent. So technically this is x to the 1st. There's a little 1 on there. So if we add the exponents, we're going to do 1 plus 2/3. I'm going to just do that off to the side. So 1 plus 2/3. Okay, so since the 2/3 is a fraction, let's make the 1 into a fraction. And to add them, we have to find a common denominator. So if this is a 3, we need to get this to be a 3. So we can get that to be a 3 by multiplying the 1 by 3. But if you multiply the bottom of a fraction by a number, you have to multiply the top of the fraction by that same number. Okay, so then that leaves us with 3 over 3 plus 2 over 3. Okay, so now 3/3 plus 2/3 would be 5/3. You add the numerators and you keep the denominators. Okay, so that would give us x to the 5/3. Okay, now let me bring down the plus 2x to the 5/3. Actually, look at this. This worked out. In order to add, you have to have like terms. And look, we do. Now that these x's have the same exponent on it, they're like terms, so we can add them together. If you have 4x to the 5/3 plus 2x to the 5/3, you just add the number in front. So that would give us 6x to the 5/3. Now, when we look at the answer choices, they have radicals in all of them. So what they did was they rewrote this using power over root. Okay, the 6 doesn't have an exponent on it other than a 1, so this is just 6 to the first. So this would just be 6. But if we do power over root, we could write this as the cube root of x to the 5th power. So the cube root of x, and you could put the 5th power right on the x, or you could put it, up here on the top of the radical. But choice 2, they wrote it like I wrote it. Okay, so number 23 wants us to rewrite this as a single term with a rational exponent. So rational just means fractional. Now, in order to, if you have two separate terms, if you want to be able to combine these into a single term, we want to get them out of radical form. So this right here is the cube root of x to the 1st power. There's really, even though we don't see it, a little 1 right there. So we could, if we were to use power over root, we could rewrite this as x to the 1/3 power. Okay, and then times. Now, this is the square root of x to the 1st power. When you have a square root, you don't really put the little 2 in there, but if it helps you out to put it there just to visualize it, this would be the square root, that's a 2, of x to the 1st power. So we could write this as x to the power over root, x to the 1/2. So x to the 1/2 power. Okay, so now, since we're multiplying two terms that have the same base, we're going to take these exponents and we're going to add them. So I'm going to do that off to the side. So 1/3 plus 1/2. So we need to find a common denominator. The common denominator is going to be 6. So I'll multiply the first fraction by 2/2 and the second fraction by 3/3. So that's going to leave me with 2/6 plus 3/6. Okay, then when you add fractions, you just add the top, so you add the numerators, and you keep the bottom. You keep the denominator, so that's 5/6. So we can rewrite this as x to the 5/6. So this right here, sorry, I'm going to make it a little bigger, so that actually looks like an exponent. That looks worse. So this is a single term, and we have a rational exponent. All right, if we take a look at number 24. So they give us a picture of this function here. They give us a graph of the function. They want to know which equation could represent p of x. Now, because this is multiple choice, if you wanted, you could just go to y equals and graph these one by one and see which one looks like this. But we're going to do it by hand. I want to make sure you understand really where this comes from. Okay, so what you could see by looking at the picture of this graph is that we have zeros at x equals -3. Okay, that's right here. At x equals +2, and then at x equals +3. Okay, so if these are our zeros, the factor that would go along with a 0 of x equals -3 would just be x plus 3. The factor that goes along with a 0 of x equals +2 would be x minus 2. And then the factor that goes along with the 0 of x equals +3 would be x minus 3. So if you look ahead at these answer choices, okay, you want to see which of these contains these factors. Now with choice 2 and 4, you would have to actually sit there and do grouping, okay, with both of these to factor them to see which would contain those factors. So if you wanted to do that, you totally could, but you're not even going to have to do that, because if you look at choice 1, right, see this x squared minus 9? Doesn't that factor to be x plus 3 times x minus 3, isn't that dots? And then we still have our x minus 2 right here. So don't these three factors match up with these three factors? So choice 1 would be the answer. Okay, number 25, the zeros of a quartic, so a fourth degree polynomial function, are positive 2. Okay, so let's put a 0 at positive 2, negative 2. So we have a 0 at negative 2, positive 4. So we have a 0 right here at positive 4, and negative 4. So we have a 0 at negative 4. Okay, so those are our zeros. Use the zeros to construct a possible sketch of the function on the set of axes below. Okay, I mean, so it doesn't say whether in this part, whether the leading coefficient is positive or negative. So you could sketch this either one of two ways. Okay, so you could either have it opening down, like I do here, or you could have it opening up, like I do here. Okay, so then in the next part says, given that the leading coefficient is 2, write an equation for your sketch above in standard form. Okay, so if the leading coefficient is 2, just to point out, our graph would be opening up. So because they want us to write a function, or an equation it actually says, but I'm going to write it as a function, you could write f of x or p of x. You can call it whatever you want because they don't really say. Now the leading coefficient is 2, so I'm going to put a 2 right there. And then let's just look at our graph and let's just write down what factors correspond with the zeros. So at this 0 right here at x equals negative 4, the factor will be x plus 4, right? For a factor, you reverse the sign of a 0. For a 0 at x equals negative 2, the factor would be x plus 2. For a 0 at x equals positive 2, the factor would be x minus 2. And for a 0 at x equals positive 4, the factor would be x minus 4. Now I'm going to box this off as my answer because it doesn't say you have to write it in standard form. If it said you had to write it in standard form, you'd have to multiply all this out. But because it just says write an equation, I would leave it in factored form because then you don't take a chance of making a mistake when you distribute everything out.